Okay, in a previous video I did a couple basic examples of solving three-dimensional systems with elimination and back substitution. Now I want to show you a couple maybe more unusual cases. Okay, so let's jump right into it here. So here we have a system of three equations, and if you watch my other video, or maybe some others, you know that you kind of want the first equation to have x, y, and z, the second equation only to have y and z, and the third equation only to have z, so that after you've modified the system, you have this sort of staircase look to it, okay? So that's kind of what we want to create here. So we'll get right down to it. I'm going to multiply the first row by -3 to give me a -3x here to add to this 3x. So I'll take -3 times row 1 and I'll add it to row 2 to give me my new row 2. That's going to eliminate the x in my second row. I also want to eliminate the x in my third row. So I notice that I've got x, so I'd like this in the first row to be -x. So I'll multiply my first row by -1. So negative times row 1 plus row 3 will give me my new row 3. So let's see what these look like. -3 times row 1, that's going to be -3x minus 3y minus 3z equals -21. Plus row 2, well, row 2 is just 3x minus 2y plus z equals 3. And I add those together, and you'll see that the x's cancel. And I'm left with -5y minus 2z equals -18. So that's my new row 2. Let's figure our new row 3. So I need negative row 1. So that's going to be -x minus y minus z equals -7. Plus row 3 is x plus 6y plus 3z equals 25. And the x's cancel like we wanted. And I'm left with 5y plus 2z equals 18. And that's going to be my new row 3. So row 1 doesn't change, just row 2 and row 3. So my new system, my new equivalent system is going to be x plus y plus z equals 7. My row 2 is going to be -5y minus 2z equals -18. And my new row 3 is going to be 5y plus 2z equals 18. Okay. Now I want to go about eliminating y from my third row. And I notice that I already have -5y in my second row, so I'll take row 2 plus row 3 to get a new row 3. So that's going to be row 2 is -5y minus 2z equals -18. And row 3 is 5y plus 2z equals +18. And I'll add those together. So my y's cancel, but my z's also cancel. So what do I have here? Well, -5y plus 5y, when I say they cancel, that means they give me 0 when I add. And -2z plus 2z also gives me 0. So on the left side, I just have 0. And on the right side, strange enough, I also have 0. So this is an interesting case of a system in 3 dimensions, or 3 variables, or 3 equations. We have this thing where y and z both eliminated. Okay, that gives us, and we get a true statement. When we do that, we didn't get something like 0 equals 6. Okay, we'll talk about that later. We got a true statement. So what we have is what's called a dependent system, meaning we can pick a number for x, y, or z, and then the other two variables will be based on our choice for that first variable. They will depend on that choice. So let me show you what I mean here. Let's go through this. Typically when you solve these systems, you find z first. So since it's dependent on one of the variables, let's make a choice for z. Let's assume that z is a real number, any real number, okay? The way we write that is like this. And so the way to read this is, that's just a capital R with 2 vertical lines. You just read that as z is an element of, So this symbol here, this epsilon means is an element of the real numbers. Okay? So no big deal. Z could be any number. Okay? So assume that. So we know our Z value now. So now once we know Z, we go back and we figure out Y. So Z is any real number. So then I back up, just like before, I back up to my second equation. So I know that negative 5y minus 2z equals negative 18, and I need to figure out what y is, get y by itself. Okay? So when I do that, I'm going to add 2z over. And then I'll divide by negative 5, which is the same thing as multiplying by negative 1/5. So I get y equals negative 2/5 z, and dividing negative 18 by negative 5 gives me positive 18/5. So that's my y for my ordered triple solution. Now I need my x. So to get my x, I back up to my first equation, which tells me that x plus y plus z equals 7. But then I can plug in my y value that I have, and my z is just z, so I'm not going to do anything with it. So I've got x plus my y, negative 2/5 z plus 18/5, plus my z equals 7, and I'll solve for x. Okay, so let's go about this. First thing I need to do is combine my z terms. Negative 2/5 z plus 1z gives me 3/5 z, and I'll copy down my plus 18/5 equals 7. Next, I'll move my constant over. I'll subtract my 18/5 from 7, giving me 17/5. And on the left, I've still got x plus 3/5 z. Finally, to get x by itself, I'll subtract the 3/5 z. So I've got negative 3/5 z plus 17/5. And that's my x. Okay, so let's talk about what this means. I've got x, I've got y, and I've got z. So the solution to this system, in fact, there's an infinite number of them because z could be any real number. So there's infinite solutions. And it's the set of all ordered triples where x is negative 3/5 z plus 17/5, so that's x, comma y has to be negative 2/5 z plus 18/5, and z is just itself. All three coordinates of this ordered triple depend on z. Again, that's why it's called a dependent system. And what do we know about z? Such that, so it's every ordered triple that looks like this, such that, or where, z is a real number. So what you can do, there's an infinite number of solutions. What that means is pick any real number for z and plug it in to all three of these coordinates, and you'll get three coordinates, an x, y, and a z. Those three, x, y, and z, will make the original system true, all three equations. So that's what that means. So our solutions are written dependent on z because two of the variables, remember, eliminated here, so we couldn't actually get a number for z. But we did get a true statement, so we knew we could get an answer. Okay, let's look at the next example, which is along the same lines. Okay, so we've got this new example here. Let's eliminate this 2x by multiplying row 1 by negative 2 and adding it to row 2 to get a new row 2. And to eliminate this 8x, I'll multiply row 1 by negative 8 and add that to row 3 to get a new row 3. So let's write this out. Negative 2 row 1 is negative 2x minus 4y plus 2z equals positive 16, plus row 2 is positive 2x minus y plus z equals 4. My x's cancel. I get negative 5y plus 3z equals 20. So that's my new row 2. Negative 8 row 1 times row 1 is negative 8x minus 16y plus 8z equals 64. Copy row 3, 8x plus y plus z equals 2. And then add those together. My x's cancel. I get negative 15y plus 9z equals 66. Okay? And that's going to be my new row 3. So let's write our new system. Row 1 doesn't change. X plus 2y minus z equals negative 8. 2x minus y plus z equals 4. And 8x plus, sorry, I forgot to write my new row 2 and new row 3. New row 2 is here, so negative 5y plus 3z equals 20. And my new row 3, negative 15y plus 9z equals 66. Now I need to go and eliminate this negative 15y. Okay? Maybe one thing I notice here is that in row 3, all three terms are divisible by 3. So instead of eliminating anything, I'm going to make my numbers smaller first. So I'm going to take and divide row 3 by the number 3, and that's going to give me my new row 3. You can multiply a row by a number or divide a row by a number to get a new row. So I get x plus 2y minus z equals negative 8. Negative 5y plus 3z equals 20. And then I get, divide this by negative 15 by 3, I get negative 5y plus 3z equals 22. Now my numbers are smaller. That might make it easier to work with. So I need to eliminate this negative 5y using my second row, which is also negative 5y. So I'll multiply my second row by a negative 1, and I'll add that to row 3 to get my new row 3. So negative row 2, that's going to be positive 5y minus 3z equals negative 20. Plus row 3 is negative 5y plus 3z equals 22. My y's cancel, but my z's cancel also, and we know that's 0. On the right side, however, I don't get 0, I get 2. This is a false statement. That means no matter what x, y, or z is, these three equations can't all be true. So this system has no solution. There is no ordered triple that makes it true. And it's what we call an inconsistent system. A system that doesn't have a solution is called inconsistent. And so that's what happens. In the last example, we got a true statement, meaning there's an infinite number of solutions. We get a false statement, there is no solution to the system. There's no ordered triple that makes it true. Okay, but the answer to the solve question is no solution. Not inconsistent system, that's just a name for the system, but the answer to solve is that there is no solution. Okay, so those are some more tricky examples of solving systems of three linear equations.